Okay. So let me remind you where we were. Last time we proved this lemma about bases. Mandy, do you mind closing the door? Thanks. Okay, so lemma, we called it B2 star. It says if A and B are bases of a matroid, and you have an element B which is in basis B but not in basis A, then you can find an element little a that you can swap it with in A, such that A minus A plus B is a basis. So we proved this last time, and we said that this was similar to, but different from the normal basis for the normal basis exchange axiom. In the normal basis exchange axiom, we wanted to perform an exchange between A and B, and we said if you start with a little a that you want to get rid of in big A, you can replace it with a little b in big B. That was the original exchange axiom. So maybe I should say that B2 was kind of like this. Given this guy, and given this guy, you can find an element B which is in the basis big P to swap A and B. And here we have a similar situation, but in this case, we are given the basis A, the basis B, and we are given an element which is in big B. And this B2 star says that we can find an element in big A to swap it with. So we're given this guy, we're given this guy, and this implies that we can find this guy little a. So this is the difference between the two basis axioms, and we already proved that both of them hold. Okay. And remember what I was going to do was use this to prove this notion of duality in Matroid theory. So I was in the middle of proving this theorem that said if you have a matroid whose bases are the collection script B, then you can define a second matroid whose bases are the complements of the things in B. E minus B such that B is in script B. The conclusion is that this is also a matroid, so we called it M star. We said M star equals E comma B star is a matroid. Also, this is the theorem we want to prove. And we said this is called the dual matroid. So this is what I'm going to prove now. Okay. So in order to prove that this is a matroid, I need to check the two normal exchange axioms for B star. Check that B star satisfies B1 and B2. The first basis axiom of a matroid says there is at least one basis. And we know that's certainly true because the matroid M has a basis, so its complement is a basis of B star. So because B is not empty, if you take a basis in B, then the complement is a basis in B star. And so therefore, B star is not the empty set. Okay, so again, this is kind of trivial. And now we have to check B2. Okay? And B2 says if A and B are bases, we don't know that we can call them bases yet. If A and B are in B star, and we have an element in A minus B, then we can find an element in B minus A such that A minus A union B is in B star. I'm not claiming that we know this. I'm claiming this is what we want to show, right? Want to show. Okay. This is basically the definition. And just to make the notation a little bit less complicated, I want to be able to distinguish between basis of B and basis of B star. And so what I'm going to do is that I'm going to call sets in B by letters and sets in B star by letter star so that we know where they live. So instead of calling these A and B, let's make the notation a little bit clearer and call them A star and B star. That just means that they're sets in B star. Okay. So let me just put stars everywhere. And that way I'll know whenever I have set star, I'm supposed to think that's in B star. Okay, so what does this mean? Let's unravel it. Well, A star is in B star, so it's the complement of a basis in B. So let's call that basis A. A and A star are complements, so A is in B. Okay. And let B be the complement of B star, and by definition, B is also the script B. It's by definition. What does it mean for A to be in A star minus B star? It means A is in A star and A is not in B star. Right? But then let's translate that into A and B. So what that means is if A is in A star, that means that A is not in the complement of A star. It's equivalent. In fact, let me put if and only if because these are equivalences. Okay? A is in A star means A is not in A. A is not in B star means that A is in B. In other words, what this means is that A is an element of B minus A. What am I looking for? I want an element B in B star minus A star. And by the same argument, if A star minus B star is B minus A, then that means that B star minus A star is A minus B. I want to find a B in A minus B such that the conclusion that I want is this one. A star minus A union B is in B star. This is the B that I want to find. Okay. But what does it mean for this guy to be in B star? It means that its complement is in B. It's the definition of B star. So this guy is in B star if and only if the complement E minus A star minus A union B is in B. It's just by definition, right? But what is this? This is E minus A star union A minus B. And E minus A star is A. So this is really A union A minus B. Okay?
Federico?
Yeah?
What's equal to A union little a minus B, the whole thing, or just the parenthesis?
Oh, so this whole thing is equal to this.
Oh, okay, thank you.
Because E minus A star is A, and then you got rid of getting rid of A, so that means you added A, and then you got rid of B, so that means you got rid of B. So these two are exactly the same set. And so now basically what I did is take this statement about B star and translate it into a statement about B. What does it say? It says, I'm given A and B and B and B. I'm given A and B minus A. So let this guy, and this guy. And I want an element of A minus B such that this happens. So let's see what I'm doing. I'm given two bases A and B, and I'm given an element in B minus A that I want to add to A. And this is telling me I want to find an element B that I can swap it with. An element B and A minus B that I can swap it with. In other words, if you look at this blue statement, this is exactly the statement B2 star. And in fact, if you want this statement B2 star to look exactly like what I have here, all you have to do is just change the names of A and B. So if you just call this guy A, and just call this guy B, then that means this guy is B, this guy is A. And you see that this statement that I made here is exactly the statement that I highlighted here in blue. Let A and B, let B and B, let little a, B, and B minus A. Then I can find B and A minus B such that I can perform the swap. Exactly what I have over there. Okay. So in other words, what I want to show is B2 star, which I already did. So this is true by B2 star. End of proof. Any questions about this proof? So let me just make a comment about how you come up with a proof like this. I mean, remember that in the last class I said that I wanted to prove this theorem about duality, and the way that I was going to prove it was using 3 steps. So you should look back at your notes from last time and see that I said 3 steps. The first step was a lemma about circuits. The second step was a lemma about bases. And the third step was actually proving the theorem. How did I come up with that proof? Well, I said, let me try to prove the theorem. And when I go to prove the theorem, well, the theorem says something about B star. I translate it into something about B, and I see what I need to prove about B is exactly this thing. Okay, so this is not just something that I pulled out of nowhere. This is exactly the statement that I needed to prove in order to prove duality. And then I said, okay, how do I prove this statement? And then I might have thought, well, this is just as easy as the normal basis exchange. And then after a while, we see, actually, it's not so easy. And to do it, we need this other circuit lemma. Okay? And the circuit lemma is exactly the one that I kind of circled for you guys, and I said that you should discuss it in the forum. Okay? So this was the key of the proof. And so then that told me, okay, I should prove that lemma about circuits. And this is what you should always think when you're reading a proof in Oxley's book, or in just about any other math book. It's always going to be like this. They say, okay, lemma, and you say, okay, I don't see where this lemma comes from. And then you say second lemma, and you don't see where that comes from either. Well, it's good if you can follow the argument logically and follow what they're saying. But it's often going to be more instructive if you just try to prove it yourself and say, okay, let me try to prove it and see, oh, what I need is lemma 2. And then you try to prove lemma 2 and say, oh, what I need is lemma 1. And then not only will you be able to follow Oxley's proof, but then you'll see where on earth he got it from. Okay? Of course, this is exactly the kind of thing that you're going to be doing in the homework. I ask you to prove something, and it's something about matroids, and so you're just going to keep reducing it to simpler and simpler statements about matroids. Question, Curtis?
Your shorthand there with bottom left over there.
You're asking me about this shorthand.
Yeah.
It's totally confusing, right? I agree with you. I think I got a little bit too lazy, so let me say it in words, and this is a shorthand for what I'm going to say in words. But so you should pay attention more to the words than to the schematic thing here. So axiom B2 says this. It says, if I have two bases A and B, and I want to kind of perform a swap from an element of B to an element of A, okay? B2 says, if I have two bases A and B, and I've decided which element in A I want to get rid of, then no matter which one I want to get rid of here, I can replace it with an element here in B minus A. So in other words, you're given the element you have to get rid of in A, and you're asked to find an element in B to replace it with. B2 star is very similar, but the opposite in a way. You're given A and B, and you want to perform an exchange again. And in this case, you're told you have to add element B from B minus A. And then it's your job to find an element A in A minus B to swap it with. Okay. So this is why I have this arrow going from A to B saying, I'm given A in this case, and I want B. And B2 star says, I'm given B in this case, and I want A. And you'll see that problem 6 in homework 2 is very related to this and says in a way that you can take an arrow in both ways. And I don't think everyone has had a chance to think about problem 6 in the homework, but you'll see that it's very similar to these two axioms. Okay? And I'll be happy to talk about it later on when you've had a chance to think about it some more. Okay?
Homework today.
No, it's due a week from today. Good news, huh? Yeah. Now remember that so I said that on the website, and the homework is due every 2 weeks, which is why they're kind of long, because you have 2 weeks to do them. So, so you have a whole other week to think about this. Okay, so
have we covered everything it takes to do homework 2 at this point?
Yes, we have. You're ready to solve homework 2. As you saw last time, it's not a matter of knowing techniques. I mean, I have solutions for you guys, and actually I should tell you, I posted solutions on the website for homework 1, and they're all your solutions. I didn't have to add anything because you guys solved the whole homework, and there weren't any ideas in there that you didn't know, but you saw that it was work. It was hard work, and it's the same with this one. You know how to do it. I mean, you have the tools to do it, but you don't know how to do it yet, and so make sure you spend some good time finding a way to use the tools that you do already have. Okay. So there is duality. And so we showed that matroids have a notion of duality. And the reason that people like to call this duality is that usually with dual objects, you want the property that the dual of the dual is the object. In other words, if you start with a matroid and you take the dual, and you take the dual again, you get back the matroid. The dual of the dual of M is the same thing, M. Okay? And this might impress you or it might not impress you. I mean, it's nice when mathematical objects have a notion of duality, and I know, for example, that several of you have taken courses in advanced linear algebra where you see that there's a duality between a vector space and its dual. You have a vector space, V, and then you have a vector space V star, which is the vector space of linear functions on your vector space V. And this has the property that linear functions on V are just elements of V. This is not entirely obvious, but basically what I'm saying in a way is that vector spaces have the same nice notion of duality.
So I suppose it's true also for matroids defined in terms of its circuits. The duals of those would also be matroids.
So you have to be a little bit careful, but yes, I mean, so if you start with a collection of bases and you take the complements of these, you get the basis of a second matroid, the dual matroid. If you do that with circuits, that's not going to work exactly. So if you start with the circuits of a matroid and you take the complements of those, you're not going to get the circuits of a matroid. But there is a way of saying if the circuits of a matroid are these, C, then the circuits C star are something. They're not the complements, they're something more complicated.
So it's true for certain sets of circuits.
Right, and so the point is that there is a dictionary that says, there's kind of the matroid M, there's a dictionary between the matroid and its dual. So, you know, in the original matroid you have matroid and the dual. So here, for example, you have a collection of bases, and we know already the bases of this guy are the complements of the bases. So that's your dictionary to go from bases to bases. So the next question is, okay, what about if I start with circuits? What are these guys? It's not so simple, but you can say, okay, circuits are the things that satisfy something in terms of C. Or you start with the independent sets here, then you can tell me what the independent sets here are. They're something. And it'll take us some work to come up with a whole dictionary. So far, the only thing we know is the first entry of this dictionary. To go from basis of a matroid to basis of its dual. Okay? But before we spend a lot of time developing this notion of duality, well, I want to somehow make the point that this notion is actually important. So how good is this notion of... Actually, before I even do that, let me just do an example to say that, to make sure that we're all clear. And let me just repeat the example that I did last time where let's take the matrix that we keep talking about. So the elements are A, B, C, D, E, F. And again, let me define it in terms of bases so that it's easier to translate to the dual. So the bases of this guy that we keep talking about are A, B, C, A, B, D, A, B, E, B, C. No. A, C, D, A, C. And we saw that one of the ways of thinking about this matroid is to draw the graph. A, B, C, D, E, F. So what is B star? B star is the collection of complements. So the complement of ABC is D, E, F. The complement of ABD is C, E, F. The complement of ABE is C, D, F. This one is B, E, F. And this one is B, D, F. Okay? So my theorem says this is a matroid. And in fact, I showed you last time that it's a graphical matroid because I showed you a graph that has this matroid. But I think it was Just Deep who made the point in the forum that there were several choices for the graph that I could draw here, and there's one that she would prefer much more, which is this one. Okay, looks familiar, but the only thing is we have to change the names of the elements. So if we call this one F, this one A, this one D, this one E, this one B, and this one C, and we look at the spanning trees here, well, they're exactly these: D, E, F, C, E, F, C, D, F, B, E, F, and B, D, F. Okay. Now, I want it to be very clear to you guys that this is just total luck. It's never going to happen. I mean, it's going to happen sometimes, but it almost never happens. This is an example of a matroid where this is a matroid that is isomorphic to its dual. Why? Well, look. What does it mean to be isomorphic? It means that I can kind of relabel the elements and get the same matroid. And here's the relabeling. I'm going to call A F, I'm going to call F A, I'm going to call B D, and so on. And the matroid that I get is the same matroid, except I have different names for the elements. In this case, okay. But this is very rare. But a matroid with this property is called self-dual, such that it's isomorphic to its dual is called a self-dual matroid. By self-dual, I mean basically that it's dual to itself. If you take the dual, you just get the same matroid except with different names. Okay? This is a definition. Matrices that are self-dual are very rare, but they exist. And one of the questions that I posted also in the forum is can you find other ones? This is a good, interesting question. And maybe you can tell me why these two happen to be, why this happens to be a self-dual matrix. Maybe you can find other ones. Maybe you can find infinitely many, because there are infinitely many self-dual matrices. So that's a good question to think about, is how can you come up with matrices like this? Okay. And as we discussed very briefly last time, this notion of duality opens up a million questions. So for example, question, is the dual of M, I mean, if we did this example, maybe we would think the dual of M is always isomorphic to M. Always isomorphic to M. Well, I told you that the answer is no. This almost never happens. But you might relax the question a little bit and say, okay, I started with a graph. So I started with a graphical matroid. I took the dual, and I got another graphical matroid. So maybe that is true. Question, is the dual of a graphical matroid always graphical. It is in this example. But what do you guys think the answer is to that? If I asked you to take a wild guess, you think this is a coincidence? Well, you're right. No. But often it is. And we'll say what this means. Now, what other properties does that matroid have? Our example. For example, we saw that it's a linear matroid. So maybe I'll ask the question, okay, is the dual of a linear matroid always linear? And if I ask you to take a wild guess, would you say that that's true or that that's not true? You think it's true? And some of you that think it's not true. There's no necessarily compelling reason to believe one or the other, but it turns out the answer is yes. So we're going to see that if you start with a matroid that is linear and you take the dual, then that's also linear. Okay. So a third question you could ask, which is that, remember this matroid is also transversal. So what about that? Is the dual of a transversal matroid transversal? If I asked you to take a guess.
Open.
I'm sorry?
Open problem.
Open? It's not open, actually. So actually, this is also not true. No. But this question is very interesting, and we'll say more about this. But this is also an interesting question. A very interesting question. Is what can you say about duals of transversal matrices? Okay. I'm sure you can come up with a million more questions, and these are all good questions as long as we agree that duality is a nice thing. If duality is a boring thing, then there's no reason to care about these questions. Okay? And so the next point that I want to make is that duality is actually an amazing, amazing notion. But really the big question is, how interesting is matroid duality? How interesting, how useful. And this is something that you cannot just tell from this definition. I mean, okay, this is kind of nice, I think you'll agree that this is a nice property. Maybe it's not terribly useful, but it turns out to be just an amazing notion. Very. And the reason that it's very interesting let me give you two reasons very quickly. What about vector space duality? So vector space duality is a pretty fundamental notion, and you know that if you have a vector space and you have a subspace of it, then that subspace has a kind of a dual, which is what? The natural. So you can word it you can phrase it in two ways. But the point is, if you have a vector space and you have a subspace, then there's a natural subspace that is associated to it, which is the orthogonal thing, the orthogonal complement. If you want if you're not in a Euclidean space, then okay, maybe orthogonality doesn't make sense, but you can go to the dual space and do the same thing. In fact, I propose that one thing we should do in the forum is talk about dual spaces so that people see that they shouldn't be scared of them, and that the dual spaces just behaves in almost the same way as the orthogonal complement. Now, the point is that this is exactly generalizing that. So the reason that the dual of a linear matroid is linear is because a linear matroid is the matroid of the subspace, and the dual is the matroid of its orthogonal complement. So the matroid for linear matroids duality equals orthogonality, orthogonal complements. In other words, this completely combinatorial definition tells you about orthogonal complements, and therefore orthogonal complements do not necessarily depend on coordinatizations. They're really, you can talk about them in a combinatorial way. Okay. So any theorem that you prove about dual matroids gives you a theorem about orthogonal complements, which are pretty fundamental objects. And also for graphs, there's a notion of graph duality, and I don't know how many of you have seen that before. Has anyone seen that before? You've seen that before. Some of you have. I'll show you how that goes. The reason people normally introduce this is to talk about this question of coloring maps. And so, I don't know. Can't really draw the map of the US. Too difficult for me. So maybe I'll draw a rough map of North America here. So this is Canada. This is the US. And here's Mexico over here. Then here's, kind of embarrassed now, Guatemala. What goes next? I think here's maybe Honduras and El Salvador. I don't know. Skip something. I don't know the order very well. Then here's Panama. Then here's Colombia. That I know. Nicaragua is in here somewhere. Venezuela, Ecuador, Peru, Brazil, so on. So there's a map of Argentina, Uruguay, Chile. Okay, so on. So this is kind of a graph in a way. If you kind of say, okay, these are. So on. These are vertices. These are edges. Okay? And you can make a dual graph where it's going to be the red graph, and you're going to have a vertex in each country. Okay, so here's a vertex. It's a vertex. It's a vertex. So far, it's kind of a boring graph. Okay, let's put one for the ocean.
You have to put two oceans, or just the Panama Canal?
You know, exactly. So that's a good point. Panama Canal is right there, and so that means you don't need another one for the other ocean. And anyway, I mean, you can wrap around, and so that it's really the same country in a way. And what are the edges of this graph? Well, whenever you have two neighboring countries, you join them. So for example, Colombia and Venezuela are neighbors. Venezuela and Brazil are neighbors. Peru is neighbor with everybody around here. Colombia and Ecuador are neighbors. Colombia and Panama are neighbors. What do we do here? Panama is split into two. This means that this is... no, for example, there's a Pacific coast here in Colombia. So that means I have to say these are neighbors. But there's also an Atlantic coast in Colombia. It's the one country in the South America with 2 coasts. And so that means I also have to join here through the canal. So Panama has a bunch of coasts. You know, here's one, then here's another one, here's another one, 4 coasts, right? Then through here. You see the point? The point is, for each 2 countries, you join them if they're neighboring. Along each border, you have to draw an edge. In other words, along each black edge, you have to draw a red edge. So, for example, here's a black edge, so I need one like this, so on. Okay. We'll say more about this, but the point is that if you have your graph G and your graph G star, then G star is called the dual graph. And duality in graphs has the property that it's a duality, that the dual of the dual is the graph. And the amazing thing is that this is also a special case of Matroid duality. For graphs, duality in Matroids equals graph duality. Okay.
So
Chris.
the reason that graphical matroid is isomorphic to itself is because the dual of that graph is actually itself.
Exactly, and well, not exactly actually, because if you look at how I drew this graph last time, and if you look at how I drew it in the notes, I said I'm going to draw this in a suggestive way because I wanted it to look like the dual. But you'll see that actually the dual graph to this one does not look like this. It's different. It has the same matroid, but it's different. Okay. So really that's not the reason that this guy is self-dual. I mean, the dual of this one is a graph because I have graph duality. But the reason that I get the same matroid is not so clear from that point of view. And there's another thing. I think you're going to ask me what I'm going to say.
Well, yeah, because you said the dual of a graphical matroid is the dual graph, but you have over here that the graphical matroid, the dual is in a certain graph.
Right, and that's the next natural question is how. I mean, it seems like I lied to you, because I told you 2 things. First, I told you that if you want to take the dual of a graph, you just do it in this way. So I showed you how to go from a graph to its dual. And I also claimed that this is matroid duality. So then why did I lie over here and say that the dual of a graphical matroid is not necessarily graphical? Does anybody see why this might be a problem? Does anybody see why I'm not really lying to you, even though it seems like I am?
It seems like if the dual of a graphical matroid is graphical, then it corresponds with this. But if you don't have a graphical dual, then you can't.
But you would still have a dual graph.
But yeah, I mean, so here I said, okay, here's a graph, and I told you the procedure to get the dual graph, and I told you that the dual matroid to this graphical matroid is this graphical matroid. Okay, it's kind of sketchy, I don't know. It's kind of strange. Well, the problem is that I can do this if I have a drawing of the graph. Right? Here's a drawing of a graph. But remember, a graph is some abstract definition that says, okay, here are the vertices, here are the edges, and the question is, can I draw it? Can I draw every graph? Well, this is kind of a strange question. Can I draw every graph? Well, yes, but not in the way you might want to. So for example, and maybe I'll challenge you guys. Everyone try to draw the complete graph on 5 vertices. But try to do it so that things don't cross. Edges don't cross. So K5, the complete graph on 5 vertices. You have to have 5 vertices, and you have to join every pair of edges, but you don't want edges to cross because you don't want to create new vertices.
So you can go around and create.
So maybe you do like this. Okay, I start like this. Then maybe I'll go and draw this one. Then I say, okay, I might be in trouble here. I need to join this vertex and this vertex. I can't do it through here. Well, I have to go around. So far, I'm okay. But I'm not done. I have to join this vertex and this vertex. And I can't do it through the inside, so I have to do it through the outside. And I still have to join this guy and this guy. But how do I do it? I mean, do I do it through here? No. This doesn't work. Do I do it through here? This doesn't work. I'm stuck. So fact is that this is not just because I couldn't do it. It's just not possible. I cannot draw K5 and make it look like a map without crossings. On the plane, without crossings. I showed you how to take the dual of something that looks like a map of the world. Anything that looks like a map, you can draw the dual. But here's a graph that you cannot draw it and make it look like a map. And here's an example of a graphical matroid whose dual is not graphical. So for example, and this I could basically leave it to you as an exercise, but we'll talk about it more later. But the dual of this graph is not graphical. And the reason it's not graphical is basically this one, that I just cannot draw it on the plane. Question, Kim?
Is that in general true? I mean, this is so there are planar graphs and not planar graphs. And is it true that the ones that you can't do are always the not planar ones? Or are there some non-planar graphs whose dual is in fact planar?
Right, so in fact, let me make a definition. So what's this word planar that Kim is using? Definition. A graph is planar if you can draw it on the plane, basically. A graph is planar if you can draw it in the plane without extra intersections. When we go to really talk about this theorem seriously, I'll make this more precise. What does this exactly mean mathematically? But the point is just that you cannot draw it and form in. I mean, a graph is planar if you can draw it and it looks like a map. There's no extra intersections. So the theorem is that the matroid, the dual of, in other words, take a graph. Let G be a graph. And let this guy be its matroid. Matroid of G be its matroid. Theorem, this guy, the dual of this guy is graphical if and only if G is planar. So what this is saying is I showed you how to take duals of maps. That works. And so the content of this theorem says basically if it looks like a map, you can do the dual of a map. But if you cannot make it look like a map, then you just cannot define its dual in a graphical way. Okay? So this is one of the big theorems in kind of the Matroid theory point of view of graphs.
So Matroids aside, you can't actually define a dual of a graph that's not planar. There's no sense of it. You have
That's right. So in graph theory, when they talk about duality of graphs, they always assume that it's a planar graph to begin with. Okay. Curtis.
When you took a dual of a graph, you were just taking a vertex inside of a cycle. So not all graphs have cycles.
Exactly.
Where would you choose your vertices?
For example, what's the graph of this? What's the dual graph to this graph?
Bunch of loops.
So how many regions are there? There's only one region. And okay, here's the region is neighbor to itself. So I have to make a loop here. The region is neighbor to itself to here. So I have to make a loop here. The region is neighbor to itself, so I make a loop. The region is neighbor to itself, so I make a loop. The region is neighbor to itself, so I make a loop. And that's the dual. So it's a weird dual, I agree. But that is the way of defining the dual of this, and it works. Okay. But the reason that I want to give you a little preview of what we're going to see later is to make the point that actually Matroid duality is amazing because it's a combinatorial way of realizing that orthogonal complements in linear algebra and this procedure of taking dual graphs are exactly the same procedure. And so we shouldn't be proving theorems twice. You shouldn't. If the linear algebra people already proved it, then the graph theory people can just take that theorem because it's the same theorem. So we'll say more about this, and see you guys next time.
Was he impressed by the system works?
And he's playing with
What are you up to?
good buddies.
Oh.
She said, actually, it's almost easy. It's easy, actually, because he gets hands done around the house when they're sitting there playing.
She's not
And I
having
said, well,
that
I'm
all the time.
well, no, she's not having to entertain her daughter all the time. His daughter was sick.
Oh, I thought you said her little friend was a boy. That's what I was doing.
And then she says, furthermore, I told her I went by the library yesterday and took some videos. And so I said, you can just walk over to my house and stick them all in bed with the videos and photos. So I'm going to head home now and give her a break this afternoon.
I hope you feel better too.
Thank you. I think her well, it's crazy. Stay healthy.